In this video, we'll talk about a proof of Rolle's theorem and why it should be true. So I gave some hints before as to why this should be true. The main idea was that if my function starts at a, at the left endpoint, and goes up, it's going to have to turn around at some point. And that point where it turns around must be a horizontal tangent or a point with the derivative of 0. The same idea holds if I start going down from a, I will also get a horizontal tangent where I have to turn around to come back up. The idea there is still the same. Let's write out an actual proof as to what this looks like. First, let's recall our assumptions. We are assuming f is continuous on a b, and it's differentiable on the open interval, and that f of a equals f of b. All these will come into play over the course of the proof. So proof. Well, since f is continuous on the interval a to b, we know it attains its max and min values. That was the idea of the extreme value theorem. So since f is continuous on the closed interval, we know f attains its max and min values on this interval. Now here we have two options. Option 1 is at least one of the max or min is on the inside of the interval. Well, what happens here? In this case, we know that this max or min must be at a critical point, because that's how our local extreme value theorem worked. If it was inside, it had to be at a critical point. Well, at this critical point, we either have that f prime of c does not exist, or f prime of c equals 0. But because my function f is differentiable everywhere, I know this not existing is not an option. Therefore, I can cross this one out, and I'm left with just f prime of c equaling 0, which is what I wanted to show. Now, there's one thing that we haven't dealt with yet, and that's option 2, which is both the max or min occur at the endpoints. This works out fairly nicely. So since f of a equals f of b, that is, the value at the endpoints are the same, the fact that the max and min are both at these endpoints means the maximum value of f equals the minimum value of f. What does that get us? Well, if the max value equals the min value, this means my function is always the same value. So my function f is constant. And we know that constant functions have derivative of 0. In fact, they have derivative of 0 everywhere. So we don't just get one point where there's 0, we get that there's 0 at every point inside the interval, which clearly shows there is a point where f prime is 0. And there's our proof. Now, for anything like this in any theorems you see in math class, especially calc classes, assumptions are super important. It is always important to make sure that your function, or whatever you're looking at, meets the assumptions before you try to apply the theorem. So for instance, we'll draw a couple graphs here. In each of the examples, we will see that the assumptions are broken, and therefore we don't get the final conclusion. So for this first example, we have a function that's not continuous, because there's the jump down there, and there is no point with a horizontal tangent on this curve because I have a jump. For the second one, we have a corner, which means my function is not differentiable here. So again, no horizontal tangent. Right, the point here is critical points could occur where the derivative is 0 or does not exist. Here it just happens to be it does not exist. And so I don't get the 0, but I do still get the critical point and everything else works the way it should. I just don't get the right conclusion because I didn't meet the right assumption. Last example works sort of the same way. Again, there was a discontinuity here. So again, I don't get a horizontal tangent. There's the idea of how Rolle's theorem works, as well as what you have to be careful about when you're trying to apply the theorem to make sure you're in the right situation where you can actually apply it to get the right conclusion out of this theorem.